Next speaker, right?
That's correct.
So sorry for this small interruption because I was loading my presentation. So again, thank you for the invitation for this event, for this conference. So I was challenged to make a keynote lecture in this conference. Okay. Since the conference is about risk analysis and safety of complex structures and components, I was looking for my history, for my research background, and I found a lot of, projects, let's say, about this issue, the safety of large components and structures. So, and all are related to fatigue. So I decided to bring today an overview to you about this experience. So in this first slide, you can see also another co-author, José Correia, you know very well. So he's one of my brilliant PhD students. Nowadays is independent and is organizing this symposium. Thank you, José, for making part of the team and for this initiative of this symposium. So I'm coming from the University of Porto. We organized the first symposium, and now, so for those that are not yet aware of our city, we are in Iberian Peninsula in the Northwest region, well, next to Spain. And so the city, as you can see, I think it's interesting to visit. It's beautiful. Yeah, you should visit if you have that opportunity. And this year, as I told you before, we have a conference program here in the front of the river. So it will be in a very nice place in the old harbor. And our university in Portugal is not the oldest one because we have Coimbra, which is 500 years old, but is one of the most important in engineering in the University of Porto. So this is basically just my introduction. So I'm a professor at the mechanical department, but in my field, I've been collaborating a lot with colleagues from civil engineering department as well. So because we are talking of large structures, sometimes mechanical and civil engineers must speak to each other in these topics. So this is the topics of the presentation. I will start with a very short introduction. Then I will show you some experience in the group about pipelines. So we had in the past a project on ultra-low cycle fatigue behavior of pipelines. Then I will speak a little about welded joints. So we use a lot of welded joints in everywhere. Metallic construction. So we did some work on that topic as well. And then I will go to bridges, metallic bridges. You saw that picture from Porto City, that very lovely bridge. So this is a centenary bridge that we want to preserve. Nowadays, it's serving the metro. So it was designed by Eiffel in old times for carriages with horses. Nowadays is serving metro. So, but to assure safety, we need to stand the bridge many times and retrofitting the bridge just to allow enough or the required safety. Then a more recent project, these cold form profiles, which are nowadays very used in warehouses where we store the goods for the electronic, let's say, commerce, which nowadays with pandemic, we feel that this is very important and critical for our society. Finally, some conclusions. So this is a long presentation. I will try to make just some, show some results of those projects. Most of them were European funded projects. And as I said, they are all about fatigue. So fatigue is one of, let's say, allow me to say that it's one of the main degradation mechanisms for structures under cyclic loadings. So it represents fatigue or leads to very significant costs to the society, and we must be prepared for addressing this issue. Usually, when we are talking of design, sorry, the computer is okay. When we are talking of design, of fatigue design, we usually rely on design codes. There are many design codes, but those design codes are mostly based on what I call the global fatigue approaches. So basically, we need to test in laboratory large components, let's say structural details, to get SEM curves. From that, we try to classify the details about their severity, about stress concentrations. So we classify them in order to try to reduce their needs about the number of tests. Then we try to group materials in very broad, sometimes groups like steels, aluminum alloys. Then we rely on stress analysis, but usually we try to use non-local stresses like nominal, when I can define that. And whenever we want to improve the design, to bring a new idea for design, we may be in troubles because maybe our detail is not foreseen in the previous catalog. So how to solve this? There are two ways. We can keep on these global approaches, and we may need a lot of money to run tests and to certify the new design. Or what I am saying or defending now, we may rely on material properties, and that could be some very simple and standardized procedures to get those properties. I'm talking of smooth material fatigue tests, fatigue propagation tests. So we could characterize the material, but then we must transfer this knowledge from the material to the structure. And in that way, we will need fatigue models to make this transfer. And of course, we will need also some numerical modeling to get local fatigue parameters like stresses, strains, energy, fracture parameters. So, of course, local approaches are not, let's say, perfect, but could give us some flexibility for designing new systems. So this is what I'm going to talk about today. So I will give you some examples of the application of these local approaches to the different structural and mechanical systems. So I will talk first on pipelines. So we had a program some years ago in a European project that we coordinate in our faculty about ultra-low cycle fatigue of pipelines. We were at that time thinking on the cyclic actions on pipelines, seismic behavior, but this project was more focused on the strength prediction. Then some notes about welded joints, and bridges. So welded joints could be used on bridges, but we have also some work on more traditional bridges, those that we have many of them across Europe, made of rivets. So we want to preserve that. We must still operating our infrastructure or our transport system in those bridges. And finally, the more recent experience in direct structures. So about ultra-low cycle fatigue, we are talking of a damage mechanism in the transition between what we know the low cycle fatigue and the monotonic fracture. And on the left, you can see a typical fracture surface from a ductile steel. So where you can see this dimple type of microstructure. And on the right, you can see what we could get from an ultra-low cycle fatigue testing, where we can find in this cyclic testing, we can also find some dimple formations, which tell us that we are talking of a transition damaging mechanism. So we must understand during this cycling process, this extreme cycling process, that somehow we will get some mixture, and we must rely also on the knowledge from the ductile fracture. So in this was a European project that we ran, and in this project we developed different models, but one of them, in my opinion, the simplest one that could be well suited to be, for example, included in the future design codes, which correspond this model to a modification of proposal that was previously developed by this researcher, Chu. So in this model, we did some changes. First, or modifications. First, we transformed this model in a multi-axial model, damage model. So we incorporate here this equivalent strain definition, plastic strain definition, that is suggested in the ACME design code. Then this equivalent plastic strain range was divided by the fracture strain of the material, which actually depends not only, well, it depends on the stress triaxility and other stress parameters like the load angle. So in that case, we adopt this Bierz-Vicky approach for the fracture strain. So in that way, our model, our fatigue model, is multi-axial one, and also depends on the stress tensor triaxility and third invariant. So we can, after this, we went to the laboratory and we did some tests in order to identify our model. For that, we will need to run some static fracture tests in order to get the fracture strain. So in this case, you can see for the X60 still, the fracture locus, where you can see the fracture strain, and this is plot against triaxility in one axis, and the other the load angle parameter. And you can see that the ductility of the material is not a constant. Okay? So we may have a lower bound and a upper bound depending on the stress. If you are, for example, in plane strain or plane stress, so as you for sure know. Then we need to run cyclic tests, fatigue tests, also covering different stress triaxilities and load angles. And with that, we were able to identify our model. And this approach will lead us to the concept of we are used to use the SN lines. Now we are suggesting the use or the definition of the surface SN surfaces, where you are adding a third dimension to the SN line, which could be this stress state parameter, triaxility or load angle parameter. Okay, this is the material characterization. As I told you before, this is
one of the ingredients that we need for our local approaches. Now we must go to the, let's say, the components. So in this project, we have the opportunity with other partners, in this case, ArcelorMittal, to run some large tests on pipes. So we test two kinds of piping components, straight pipes and also elbows. Here, I will just show you the straight pipes, which were banded, cyclic banded, in order to get a very small number of cycles to failure in the regime that we call ultra low cycle fatigue, which is below 100 cycles, more or less. So, and then we went to the modeling. So again, we need material model. Then we need to run a precise numerical simulation of the structural components. In this case, we model the pipes using cyclic plasticity, using kinematic hardening, Chabot normal, nonlinear kinematic hardening. And one key point of this simulation is to capture the plastic instability. Otherwise, you cannot detect the strain localization, and you will not be able to succeed in the fatigue simulation. So we did that. So I'm just showing two results. In this graph, you can see the bending moment applied to the large pipes against the number of cycles. You can see this bending moment reduction, which corresponds to the starting of plastic instability, which was captured by numerical modeling. And then we were able to predict the fatigue life with a very narrow error margin. So we did that for two materials, two pipeline steels, X60 and X65, with different dimensions. And it was possible to get very accurate predictions. So error of one cycle in 12 or two cycles in 39. So this is, we have published a book about this. So if you want to have raw data or more information about the project, I can give you details later. So now I'm moving to the welded joints, fatigue behavior of welded joints. In this case, I started, I can say now, a long time ago, more than 10 years, collaborating with a colleague from the United States. So it was a few years after my PhD, because I did my PhD in fatigue of pressure vessels. And I did a lot of tests and on welded joints. And at that time, I learned about this colleague who worked, Ping Shadong, from the United States. And he was developing a new concept called structural stress, which is a local stress definition, again, local approaches. So in this process or in this proposal, I went later in this development, and I was sharing my data to, let's say, validate this technique. Recently, we revisited this for another application. So we start with pressure vessels. Now we are applying this to welded bridges. And here we are talking of two important aspects, two pictures. First, a stress definition, structural stress definition, which is stress linearized across the crack propagation path. That stress definition is totally compatible with the nodal forces from numerical simulation. We are not using stresses from the finite element simulations. We are using nodal forces just to get some mesh insensitivity in this process. So structural stresses in the end will be the superposition of the membrane and the bending stresses, which is a linearization of the stresses across the crack propagation path. This technology works well in the shell elements. If we are using solid elements, which are more expensive, we can use that anyway. we must transform the nodal forces to equivalent stresses in the mid plate to get in similar conditions of the shell elements. So, doing that, okay, this is one part, the structural stress definition, which is almost mesh size insensitive. The other part is the integration of the crack propagation law. So in this way, I'm not showing here the details. So a fatigue crack propagation law, which accounts for small cracks and the non-linear stress near the well toe. So that was done analytically, and we derived this, let's say, concept of SN curve, where we have a new definition for the structural stress that depends on the size of the component, like plate thickness or crack propagation size, and also information about the stress, the structural stress definition. So we have here this combination. We may have more bending, less membrane, or the reverse. So we must take that into account in our stress definition. And also if we are in displacement or stress control. So in doing that, we were able to, let's say, match in the same correlation band about 800 points, where these colored ones are from my old PhD. So recently, now with a new student, a PhD student in the civil engineering, we implemented this idea of master curve structural stress in ANSYS post-processing, let's say, model. Besides the mode 1 fatigue cracking, we added the mixed mode, mode 1 and mode 3. Leading to the effective equivalent structural stress. So nowadays, this is open for use. You can download the paper, you can install the routines if you have ANSYS, and you can run this for your welded joints. And it accounts for mode 1 and mode 3, so multi-axial process. We test this for a well-known case study from the SAE, which is a cross-beam welded, where we have multi-axial stress fields, and we have tested this with different numerical models, with different finite elements. We know this case study is available, and we know the experimental data, and we found that if we consider just mode 1 fatigue cracking, we will be not predicting correctly fatigue life, and we will be in the unsafe side. But if we consider this multi-axial approach, we will have very precise predictions for this component. After that, we were pleased with this post-processing tool. And then we moved to the bridge components. So the idea is to apply this technique in welded bridges, but since we cannot test the bridges till failure, we must rely on laboratory specimens. So we went to the literature and we found a very nice, valuable database from John Fisher from Lehigh University. This data was the basis for the current design codes, European American design codes for the welded joints. And at that time, John Fisher ran in his laboratories very important tests during more than 10 years, maybe 15 to 20 years. So we are talking of large-scale components of welded joints. And we, in that time, this was used for the application of nominal stresses and hotspot stresses. Again, in this case, we revisit this data and apply this sexual new sexual definition with the master curve concept, because we test that for pressure vessels, not for the typical details on welded bridges. So I'm talking here of, for example, girders with some attachments on the flanges, welded attachments, as you can see here. Then we have other longitudinal girders with stiffeners. And for those stiffeners attached to the web, we have some gaps between the end of the stiffener and the flanges, which generate some distortions on the webs. We have also some bracings, which increase the distortion in the flanges, or in the webs, sorry. So we also some, let's say, models from bridges to girders connected to each other with horizontal girders, connect to the with the gooses, and let's say asymmetrical loadings, generating again these distortion effects on the structure. So multi-axial stress fields. Yeah. So we were able to match all the data together. That's the most important message. And again, we superimpose these to the pressure vessels, and we found a very good correlation with the previous database. So we are adding more 300 more or less points to the existing database. So for the moment, we can say this is robust for, let's say, pressure vessels and welded bridges, where we have special multi-axial loading cases. So I guess that I over-exaggerated in the size of my presentation. I would just want to make, let's say, a few comments about, again, bridges. We started a long time ago with material characterization, again, the basis for our local approaches. So we ran fatigue tests on samples removed from the old bridges in Portugal. We did also fracture propagation tests. So the question is how to use this material information now for bridges. Prediction, fatigue life prediction. The first problem we have is a multi-scale problem. So we are talking of a very large structure, and fatigue is always local. So it happens on crystals, material crystals. So how to connect these scales? We cannot model this complete bridge at the scale of the grains. So to overcome this, we have been working in some tools. Also, in bridges, we have dynamic loads. So trains crossing the bridges at different speeds will induce different vibrations. Also, we have a lot of different trains crossing the bridges. Each day could be different. So how to solve these problems? So we cannot, for sure, we cannot solve the problem integrating the dynamic equations for this complex structure with the required fatigue scale. Well, fortunately, we can see that all these sections work in linear behavior. So the idea is to solve the problem in the frequency domains. That means modal superposition. But that is a classic technique for dynamics. But the idea here was to expand this classical idea to get the local fatigue parameters. Not stresses, not strains, stress intensity factors. Also, we need to make submodeling, otherwise we cannot solve the problem. And bad news, we have some local nonlinearities. At notches, we may have some local plasticity or contact between plates. So how to solve this? We start to run, so another student, Claudio Waters, did his PhD on this topic. So we start to run different case studies, starting with a simple beam with a moving load. That beam has some defect, the flange with a hole. And we can say plasticity is local. So we can run global elastic model, and then we can make post-processing of the the elastic stresses and strains to get local using Neuber or Glink or Morrow's equations, as you for sure know. Besides that, we can apply submodeling. And so this was done, and we proved that if we have local plasticity, we may have precise predictions of local stresses and strains using modal superposition. In this case, we were able to compare with the exact solution, let's say direct time integration, because we are just talking of a PIM. But okay, we get the Glinka's approach did very nice predictions. Neuber was not, we know, is conservative. So the deviations start after the plasticity starting to increase, which means higher loads, higher speeds maybe. When we have contact, so we can any longer apply this modal superposition. We may prepare some submodels, and in this case, if our nonlinearities is inside the contact region, we will lose some efficiency in the computation. The idea is to make the modal superposition in the local boundary conditions of our model instead of going directly to the hotspots. So this is the local submodel. And again, so I call this the approach 3. So in this approach 3, we are talking of applying modal superposition to the boundary conditions of our submodel. But in this case, you can see that using this, we will lose some efficiency, but we can get precise predictions of the local quantities. But if we have a crack starting in a rivet hole, inside a rivet head, we have contact, we have no linearities, but the crack is growing. As soon as the crack moves away from the contact region, we can go back to the approach where we can compute directly, for example, the stress-intensity factors using modal superposition. So with that, let's say, calibration, we went to the bridges. So sorry for the slides that are too dense, but anyway, we are talking of local approaches. One important message, we will not apply this as the first option. First, we should apply global approaches, and only these approaches will be applied to the critical details, okay? If from the global analysis, we will realize, okay, there should be some critical connection. Okay, in that case, we need to go locally and check with a more advanced approach. Otherwise, this will be too expensive. So this is the way we need always a global model. Then we can go locally to the rivet, and in that location, we can apply our modal superposition. The same could be applied for welded bridges. So we are talking just instead of stresses and strains, we are talking of stress intensity factors. So we can predict fatigue crack propagation in the existing bridges. Okay, finally, I would like to refer just a few, let's say, a few seconds about cold form profiles. As I told you, these kind of structures, the rack structures are using for e-commerce, and nowadays they are running 24 hours, 7 days. Loads are increasing, speeds are increasing, and design restrictions are pushing to the thickness reduction. And we are starting to observe critical failures. Well, let's say some failures in this equipment. So, and we realize that there are no design rules in our European Euro codes for these thin profiles in thicknesses sections, because the European codes were prepared for thick thicknesses. So we had this fast-call European project to check, to derive pure design rules for these cold form sections. First of all, we start with campaign of, let's say, component testing with column to beam connections, the rails, and also in parallel some small scale testing with some profiles on the right. So we did, for this, we had to develop new testing procedures because we never test those components, but we succeed. And we got a lot of data, and nowadays we can say, okay, we can propose a new design code for these profiles. So we are talking here of a lot of data, and the most important message is in this kind of seam sections, we are talking of fatigue cracking in the corners. So the corner geometry will be always a key geometric parameter. So we must be careful about that. So be careful about manufacturing, because if you are lower than R over T than 0.5, I cannot say that we can use these design curves. Of course, we are talking of, I forgot to mention, here we are using already a local stress, elastic stress in the corner of the profiles, which is a local stress definition. But anyway, we went to modeling. And in this case, since we are, I'm just finishing, just one more slide. So in this case, we have to simulate the profile production using numerical modeling, just to get the residual stresses in the corners. And with that, we applied local approaches that we listened before about the critical distances theory for fracture. Now I'm talking of that for fatigue. We applied that, and we succeed in generating, in prediction of the fatigue life of the profiles. So to summarize, as you can see, we can apply this local fatigue approach in different fields, very different fields, from mechanical to civil engineering. I have to say that this gives us a lot of flexibility in, let's say, modeling, and we rely on, let's say, more affordable testing programs. So I would recommend this as an alternative route. So thank you for your attention, and sorry for being late.